All right, good morning, Calculus 2. We're going to move into Chapter 8.2, and this is kind of where some new stuff starts here. Chapter 8 is all about integration techniques, or a big chunk of it here is about new integration techniques. We can integrate some stuff we never learned how to integrate before. And the first technique in 8.2 is called integration by parts. So it's called integration by parts, and this is the rule. If you have an integral of a u dv, it equals uv minus the integral of v du. So that's a kind of a strange looking rule. It might require a little explanation. Let's try to apply it to this problem. So this is a problem. Again, it's kind of fun to stop and realize you never really could integrate this before. It's 4x e to the 3x. Just normal u substitution or normal rules would never have helped you integrate this. And you need this new rule, integration by parts. So here's what you do. The original integral is this. And so what you have to do is identify what is the u and what is the dv. And so I'm going to call something u and I'm going to call something dv in this original integral. And that takes some experience. We can work on some guidelines, but for now, just trust me here. We're going to let u equal to 4x. And we're going to let dv be the e to the 3x dx. So that takes care of it. That's my u, and that's my dv. So that we're going to work on we're going to work on this integral. Now, as you can see later in this formula, I'm going to need a v. And to get from a dv to a v, I'm going to have to do a little mini integral right here. A little mini integral to get from dv to v. I'm also going to need a du in this formula. So how do you get from u to du? Of course, you take a derivative. So right here, I need to differentiate to get du. Du is the derivative for dx. So I did a little differentiation right there. Derivative. To get to v, I'm doing a little integral, a little antiderivative right here. And if you don't mind, I'm trying not to write all this out. I'd like to do this one in my head, so hopefully we know how to do that. When you integrate e to the 3x, it is just e to the 3x. Technically, there's a little u substitution on this little integral, and it spits out a 1/3. You've heard me say that before. And we don't bother with a plus c at this point here. We did a little mini integral right here. We integrated right here. But we don't bother with a plus c. There will be a plus c come out of this problem, but we don't need one here. Well, here we go then. According to the formula, you identify the u and the dv, you do the work to find du and v, and then you apply the rule. Here is the rule. The answer to this integral is uv. Okay, hang on, uv. Oh, here it is, uv. uv is going to be 4/3 x e to the 3x. That's my u times v. I did a little simplifying there. Minus a new integral. So here's the new integral is a v du. v du. V times this du is going to be a 4/3 e to the 3x dx. So one of the issues with integration by parts, I mean, it's just the way it is you do the integral and the formula generates another integral. So there's always this other integral you have to do to finish the problem. I mean, we did one iteration of integration by parts. And here we are, now we have to do this integral. Luckily, it's easy. This integral is, so this is my work and my notes here. This integral is easy. It's just this e function. The 4/3 is a constant you can pull out. So the answer is, moving down this way here, is this term here. And then I'm going to pull the 4/3 out in front of the integral. And then I'm integrating an e to the 3x. That's easy. We just kind of did it. E to the 3x is e to the 3x. It does spit out a 1/3 due to a little u substitution you do on the 3x. And now we're finished. Plus c. I'll just do one more move here. 4/3 x e to the 3x. We'll call that 4/9 e to the 3x plus c. So that was one example of integration by parts. And it's kind of a classic. And it can get a little worse than that. You know, sometimes what happens, you'll see this soon in your homework, is this integral that you got to do integration by parts on this. And maybe it generates another integral, and it might have integration by parts. So sometimes this can be quite layered, quite long. These are some advanced integration techniques we're learning. Let's look at another example. This one looks a little different. I'm trying to integrate the natural log of x dx. And this one's kind of quick and easy. But again, one more time, you've never knew how to integrate this before. Let me remind you what you did know. If you ever had a 1 over u du, you could integrate that. The answer is the natural log of u. So you could integrate 1 over u and you could get an answer of a natural log, but you never really integrated a natural log. We never could find his antiderivative, but you can do it with this technique called integration by parts. Again, the technique is, so I don't need this, I was just reminding you. The technique is you got to identify u and you got to identify dv. On this one, just trust me, you let u equal the log function, the natural log function of x. And then that leaves the dv to be the dx. Okay. All right, that's what you do. And here we go. When you identify u and dv, then your job is to find du and v. We find du by doing a little derivative here, 1 over x dx. I think I did, yeah, that's how you do that derivative. And you find v by doing a little mini integral here. You're integrating a 1 dx. When you integrate a 1, you get an x. Plus c, but you don't put the plus c here. All right, well, there it is. And now, I'm going to jump down here, if you don't mind, where I'm going to, the answer to this integral is here. The answer to this integral is, according to the integration by parts formula, it's uv minus the integral of v du. uv. Okay, I like to write that like this. That's my u times v, my v times u times v, minus the integral of v du. The integral of v du. Oh, that's nice. That's an x times a 1 over x dx. That x and that 1 over x just cancel. Hold on, there is still an integral there, though. You are integrating a 1 with respect to x. How do you integrate a 1 with respect to the answer is x. So this is an x, natural log of x, minus an x, plus c, and that's it. That's the answer. That wasn't too difficult. These are sort of two different little strategies here. You know, I'd like to point out, this one here was very typical. It's very typical for you to let u equal the x term, and then the derivative makes the x term go away. And then, because we had this x term which caused the integration by parts, and then when I took the derivative, it went away, and I didn't have integration by parts. You know, when I let dv be this dx and I integrate, I'm generating more x's. And that's a little counterintuitive, but in this log problem, that's how you do it. That's the way to do it. It canceled with that x, and it helped me get home. One more thing before I leave this video here. Let's just, I introduced this idea, and I did a couple examples. But I didn't prove this idea to you. Let's try a little loose proof here. You know, this idea comes from the product rule. It's kind of a, I don't know, you might want to say it's a backwards product rule. I'm not sure I want to say that. But it comes from the product rule. So if I have the derivative of a product, u times v, and I'm thinking of u as a function of x and v as a function of x. I just wrote u times v, but that's what's going on. So I'm doing a product. Okay, so what is the old product rule? The old product rule for derivatives. This is back in chapter 3. Let's see, it would be you take the derivative of the first times the second, plus write down the first and take the derivative of the second. Yeah. U prime v plus uv prime. Now, let me just write that a little differently. This is the derivative of u times v. Let me write that u prime as a du times v. And that's the derivative of u I'm calling du. Let me write the u times the derivative of v I'm going to call dv. So I just wrote those derivatives a little funny. They are with respect to x. You know, maybe you'd expect me to write du with respect to x, dv with respect to x. Let's see, what do I do now? I think I moved this term to the other side. Let's do this. So now I'll take this, I got this derivative, I got this equation. The derivative of this product is this. I'll move this term over here, subtract this. I'm going to write it as a v du, and then it equals this u dv. And now I integrate both sides of this equation. I integrate both sides of this equation. On this side, I'll have the integral of u dv. On this side, I'll have the integral of this derivative. Guess what the integral of a derivative is? The integral of a derivative will just be the uv, minus the integral of him, which will be the integral of him. Hey, I think we just stumbled upon the integration by parts formula. It came from the product rule, rearranged, and then integrate both sides. And we get the integral of u dv equals uv minus the integral of v du. That's it. That's the formula, written backwards. All right, thank you for listening. Good luck on some homework. I might have to do some more examples for you. But please ask questions when you need help.